Hello and welcome to Empowered Learning. This video is the second video in the series where we are taking the derivatives of inverse trig functions. And so in this video what I wanted to do is go over a few examples to where we actually show you how to use implicit differentiation to derive the derivative of an inverse trigonometric function. And one of the reasons why I personally think that this is important is for those of you that are not big on memorizing derivatives, or let's say you just forget, in the instance where you may be doing something to where you may not have access to a table of derivatives, you can actually come up with these derivatives on your own. So you don't have to necessarily be dependent upon a table of derivatives to be able to come up with these. So in this example, I already have it worked out, so I'll talk you through it, and then I'll go through another example to where we'll work it out together. So for this first one, we want to basically show that the derivative of arc cosecant, or cosecant inverse of x, is just negative 1 divided by absolute value of x times x squared minus 1. Okay, so we note first of all that the domain for cosecant inverse is all values of x that are less than or equal to -1 and that are greater than or equal to 1. And we note that the corresponding range is from -pi/2 all the way to pi/2, excluding the number 0. So the reason why this is again, we're going to look at the graph of cosecant inverse and show this. We'll also see whenever we do this why this negative sign is here. So let's go back and look at that. So looking at our graph of arc secant, or arc cosecant or cosecant inverse here, we see that for starters, our domain is all values of x that are less than or equal to -1 and greater than or equal to 1. And we also see that our range is all values in between -pi/2 to pi/2, but we have to exclude 0, y equals 0, because we have a horizontal asymptote there at y equals 0, or on the x-axis. Okay. Now, the other thing I want you to notice here is that this function is always decreasing. So that means that the slopes of the tangent line should always be negative, which means that whenever we calculate the derivative for valid values of x for this function, those answers should always be negative, showing that the function is always decreasing. So that's going to play a role as a sanity check for us whenever we derive these derivatives. So let's go back and actually do it now. All right, so keeping this in mind, the first thing that we know is that cosecant inverse of some value of x here, we know that cosecant inverse is just an angle. And so since we normally name angles stuff like alpha, beta, theta, I'm just using theta this time. So we're going to let theta equal cosecant inverse of x. And of course, using our cancellation property, we know that we can take the cosecant of both sides, and as long as these values of x satisfy here, we know that cosecant of cosecant inverse of x is just going to be x. And of course, on the other side, we'll just have cosecant of theta. So what we want to do now is take the derivative of this equation with respect to x. So we basically want to do this. Okay. So in doing that, we realize that the x here and the theta there does not match. So we're going to have to do the chain rule. And here's where we take the derivative implicitly. But however, we did say that x was equal to cosine theta, and that theta was also equal to cosine inverse of x. So one of the things that we're assuming here, even though we're taking the derivative of cosecant theta with respect to x, we know that theta is indeed a function of x. And that's the main point here. And so that is what allows us to be able to differentiate both sides implicitly. So just looking down here, and I'm going to get rid of this part for now. We see that taking the derivative of both sides with respect to x, on this side, we're going to have to do the chain rule. And so derivative of cosecant of blah, we know that derivative of cosecant is just negative cosecant cotangent. So that's what we have here. And our blah here is theta times the inside function, which is theta. So we'll just say d theta over dx. And of course, we don't want to take the derivative of theta because that's actually what we're trying to find. So we want to leave it in this form. On the right side, we see that derivative of x is just equal to 1 with respect to x. And so in this next step here, what we'll do is divide both sides by negative cosecant theta cotangent theta. And so we see we have negative 1 over cosecant theta cotangent theta. So now at this point, we have a way to express the derivative of cosecant inverse, because we know theta is cosecant inverse, but it's in terms of trig functions. But we need it to be in terms of x. So we have to go and translate what all that means in terms of x. So we know that we define cosecant theta as x, which is the same as saying x divided by 1. And of course, we know that cosecant is the same as the inverse, the reciprocal of sine. So that means that sine is the same as 1 over x. And sine is opposite over hypotenuse. So if we're looking at a right triangle that would model what we're doing here, and I'm looking at it as if it's in quadrant 1, because I know for sine, we know that sine inverse is good for angles that are in quadrants 1 and 4. And so that is what I'm trying to show here. Now, the main point is that my y, or this side of my right triangle here, is going to change sign, but, the vertical, that's what I mean. The vertical part of this may change sign, but what I'm calling y here, which is this horizontal component here, will always be greater than 0. In other words, always be positive. And so that part is important. So using Pythagoras Theorem, we know that, of course, since sine of 1 over x means 1 will go here and x will go here, then from there we can use Pythagoras Theorem and figure out what this y would be. And y is just going to be a positive square root of x squared minus 1. And of course, that's what this side will end up being. So we end up having this right triangle here with these sides. Now, also notice that x is the hypotenuse of a right triangle. And since it's the length of the side of a triangle, x must always be non-negative. Actually, x must always be positive, because we can't have a triangle with side 0. So here is why we want to put the absolute value on x. So probably shouldn't have written it like that, but yeah, more so like this. But that's why that x has to be absolute value, because it doesn't make sense for that x to be negative and to have a negative side of the length of a triangle, because distance can't be negative. Okay? So looking at that, then of course we have a way to translate cosecant theta and cotangent theta in terms of x. Now, the simple part is the cosecant theta. We've already said way up here that cosecant of theta is equal to x. The only thing that's different now is that we know that this part is actually going to be absolute value of x. We also know that cotangent is the reciprocal of tangent, and since tangent is opposite over hypotenuse, cotangent will be, sorry, not opposite over hypotenuse, opposite over adjacent. Then cotangent would be adjacent over opposite, which is what we see here, and that just simply simplifies the square root of x squared minus 1. Okay, and of course, here I'm just noting again what I was stating, that since this is the right side, that this is a hypotenuse of a right triangle here, x has to always be positive, and in particular it's going to have to be always greater than 1 in this case. So we end up here, and so when we put everything together, cosecant of theta is just absolute value of x, cotangent theta is just square root of x squared minus 1, and of course we know the negative has to be there from whenever we did the implicit differentiation. And so that shows us that the derivative of theta with respect to x, which is the same as the derivative of cosecant inverse, is this result as long as the values of x, absolute value of the values of x are greater than 1, which is another way of saying this here. And so that's how we come up with deriving the derivatives of this particular inverse trigonometric function. All right, so let's move on to next example, and let's do one of these from scratch. All right, so the one that we'll do together is we want to see how is it that cosine inverse of x is just negative of 1 divided by square root of 1 minus x squared. And so again, we note that cosine inverse of x, we just let this equal some value y. If we do the cosine of both sides, means that x is equal to cosine of y. And here we know that y has to be in between 0 and pi. And again, we'll go back to the graph of cosecant, sorry, not graph of cosine inverse to be able to show you why that is. All right, so you see here with cosine inverse that our graph is always decreasing, so that's why the negative that you see whenever we say the derivative is just this. Oh, sorry, I wrote that the wrong way. Let's get that right. When the derivative is this, why the negative has to be there. Again, we also said that whenever we're looking at what y is, of course, and you see y is the results for the values of x that we plug in. X is valid from -1 to 1, and our range is valid from when x is 0 all the way to pi. So that is why I have what the domain and range are in the problem that we're about to do. All right, so coming back to our example here, since we've stated here that x is going to be equal to cosine of y, we're just going to take the derivative of both sides of that equation with respect to x. And so in doing this, we know that the derivative of the left side, derivative of x with respect to x, variables match, so we do the derivative normally, and that's 1. The derivative of cosine of y with respect to x, we have to do the chain rule since the variables don't match. The derivative of cosine of y is negative sine of y. But then we have to do the chain rule, so we have to take the derivative of y with respect to x. And of course, since we let y equal cosine inverse, this is actually what we're trying to solve for. So from there, we know that derivative of y with respect to x would just be 1 divided by minus sine of y. Okay. And so looking at this, one of the hints that I give you is that sine of y is equal to plus or minus square root of 1 minus cosine squared y. Okay. And here we know that that basically comes from saying sine squared of y plus cosine squared of y is equal to 1, and algebraically manipulating that to solve for sine. The thing that we have to understand is that whenever we look at these angles here, so of course y is just an angle and x is our result here, okay? And we know that for 0 to pi, for the function cosine here, we know that cosine could be positive or negative. So that's another reason why this plus or minus is here. But we'll actually see why it ends up being negative. And that's because, again, we have this natural negative that's here. Now, if we do the right triangle thing like how we did before and just kind of look at it that way, we know that if our angle is y, and we know that cosine of y is just x, which is the same as x divided by 1, then cosine is adjacent over hypotenuse, so that is adjacent over hypotenuse. And of course, this should actually always be positive, so we could put absolute values on there if we wanted to. But again, if we go ahead and use Pythagoras Theorem, then we see that we got x squared plus y squared, which, well, let's not use y, because since I've already used that, we have x squared plus b squared is equal to 1 squared, which will turn out to be 1 minus x squared is equal to b squared, and I'm calling this b. And then that will be plus or minus 1 minus x squared here. And of course, since this is the length of the right, is the length of a right triangle, the negative part would not make any sense. So this would go away and it would just be positive. So here, we know that that is why this part here would just go away, because again, sine of y is just opposite over hypotenuse, and we see that that's exactly what we have here. B divided by 1, and b is just square root of 1 minus x squared over 1, which is just 1 square root of 1 minus x squared. So here, just noting, we could have avoided having to do this whole thing here if we just know that sine of y is related to the side of a right triangle, okay? So once we're done with that, then of course we know that we can replace sine of y with just square root of 1 minus x squared, and there we have the derivative. So again, not too hard to do, just have to make sure that you employ implicit differentiation to do it. And so with that, this concludes the video series on taking inverse trigonometric functions, derivatives, as well as deriving inverse trig function derivatives.